Okay. uh, Next, I will discuss with you the another Bayesian-based model, which is referred to as a hidden Markov model. So, this Markov model will basically tell us the probability of a sequence of random variable. So compared to naive bias, where in a naive bias we want to estimate one class based on a set of variables, okay? In hidden Markov, we want to estimate a sequence of event based on another hidden sequence. Let's take this example, for instance. Imagine you are in a closed room. There is no window, there is no door in that room, so you cannot see outside. We don't have access to check what the weather outside is. Is it sunny or is it rainy? You cannot see outside. All you have is a thermometer that can measure the temperature, the environment temperature. And then we are going to develop a stochastic model to estimate the weather outside, which is not accessible to us. So this weather is a hidden state for us, we cannot see it, based on the temperature from the thermometer reading as an observation state. So what we see is only the temperature from the thermometer as the observation state, a state that we can observe. We are going to use that to estimate what is the weather outside as a hidden state. All we have is only the temperature reading and the history of data, what is happening in the past, what happened in the past, as a basis of a stochastic model that we are going to develop. Okay. Intuitively, if the weather is sunny, the temperature will be warm. If the weather is rainy, the temperature will be cool. So intuitively, again, we can estimate the weather by just looking at the temperature from our thermometer reading, right? But unfortunately, that is not completely true in real practice. As there are some probability that the condition might be different. So for instance, when the weather is sunny, I cannot say 100% the temperature will be warm. Instead, I rather say that when the weather is sunny, I will say there is an 80% chance that the temperature will be warm and another 20% chance that the temperature will be cold. As well as when the weather is rainy, all I can say is only there is a chance of 40% that the temperature is warm, where another 60% the temperature will be cold. So higher probability of cold temperature when it is rainy. That makes sense. But I cannot say, I cannot guarantee 100% that the temperature will be cold when it is rainy. So this kind of probability, when the probability depends on another state, when the probability of one state depends on another state, this is what we call as emission probability. Okay. In mathematical form, these probabilities, let's say this 80% 80% chance of having a warm temperature given a sunny weather, we can formulate it as the probability of warm temperature given sunny weather. The counterpart, the 20% probability, can be written as the probability of having cold temperature given sunny weather. As well as the other two, the probability of having warm temperature given a rainy weather is 40%, and the probability of having cold temperature given rainy weather is 60%. Now, how do we predict the weather without opening the window, without looking at outside, without an access to the hidden state, the weather itself? Let's take a case of 6-day case here, 6-day event from Monday to Saturday, and then let's take a case again that I know the sequence of the temperature from Monday to Saturday. It's warm, cold, warm, cold, warm, cold. If I can boldly assume that the probability of having warm temperature because the weather is sunny is 100%, as well as if the weather is sunny, the temperature 100% will be cold, then I can easily say that within these 6 days the weather will be a sunny, rainy, sunny, rainy, sunny, rainy. Or can we say the same thing, knowing that the probability of having a warm weather when it is sunny is higher than having cold weather when it is sunny? As a counterpart, also the probability of having cold temperature when it is rainy is higher than the probability of having warm temperature when it is rainy. So can I just, based on that knowledge, I just say that the weather will from Monday to Saturday will be just simply sunny, rainy, sunny, rainy, sunny, rainy? Can I just simply say that? That is the question that we are going to answer using this hidden Markov model. Okay, we have discussed this. We have already talked about emission probability. There is a probability of 80% of having warm temperature given it is sunny, and there is an emission probability of 20% having cool temperature given it is sunny, as well as for rainy we have 40% of probability of warm temperature given it is rainy, and 60% for the counterpart. But what we are going to do, we are going to predict the sequence. So if today is sunny, we are going to predict what will happen tomorrow. If today is rainy, is tomorrow going to rain, or is tomorrow be sunny? So in that case, then we need another probability number. This is what we call as transition probability. So in this case, let's take an example. There is an 80% probability that tomorrow is sunny given today is sunny. Okay, so as a counterpart, of course, there will be the remaining 20% that tomorrow is rainy given today is sunny. Okay, as well as if today is rainy, then there is 60% chance that tomorrow is also rainy, and the counterpart, there will be 40% probability that tomorrow will be sunny if today is rainy. Okay, so from a stochastic point of view, from statistic point of view, this can be written, this 80% of probability of having tomorrow sunny given today is sunny, I can write it with this symbol. The probability of tomorrow sunny given no, today is sunny. So I represent today, then I plus 1 will be tomorrow. If I is Monday, then I plus 1 will be Tuesday, and so on and so forth. So for this one will be probability of tomorrow is rainy when today is sunny, and same to this, rainy tomorrow, rainy today, sunny tomorrow, rainy today. So this is what we call as a transition probability. So up to this point, we know two types of probabilities: emission probability, the probability of another event, another sequence, knowing that the other sequence, and the transition probability is the probability of what will happen in the next stage given the current state. Okay. One more thing that I want to introduce to you, this is what we call as initial state distribution. Again, let's take a case of a 6-day event from Monday to Saturday, and if we the model, the historical data should start from one event, right? So in this sequence we started from Monday. So in this case, then the first day there are two possibilities, whether it is sunny or rainy. The following day it will be defined based on the emission and transition probability that we will discuss later on. But the first day it has to start with a certain probability. This is what we call as initial state distribution, initial state probability. So in this case, let's take an example. The first day of this week, there is a probability of 67% that the first day of this week is sunny, and there is 33% that the first day of this week will be rainy. Okay, so this value pi, the initial state distribution, determine how the initial probability of different state. So at this point, again, we have emission probability, transition probability, and initial state distribution. Now we arrive to the essence of the hidden Markov model. So how do we predict the weather sequence knowing the sequence of temperature? So this is another way of saying how do we predict the hidden state knowing the observable state. The hidden state here is the weather, because we cannot see outside, we are in the closed room. All we know is the observable state, which is the temperature. So how to predict the weather sequence knowing only the temperature on this case, let's take a simple example. We have a 2-day case, 2-day event case here, Monday and Tuesday only. The observable state says that Monday is warm, Tuesday is cold. We are going to predict the sequence of the weather based on the statistic properties, the probabilities in here. So, okay. In this case, because we have 2 days, Monday and Tuesday, Monday is warm, Tuesday is cold, so there are 4 possible sequences in the air. The first sequence is when Monday is sunny, Tuesday is sunny. The second possibility is when Monday is sunny, Tuesday is rainy. The third one will be rainy, sunny, and the last one will be rainy, rainy. We are going to calculate the probability of all these 4 sequences, and then we basically similar to naive Bayes, we just pick the one with largest probability to be our predicted sequence. Let's discuss on how to calculate the probability of this sequence. I don't think I will calculate all of them, all of these 4. Let's take one specific case, the second sequence. Here we are going to calculate the probability of the second sequence. Okay, I redraw it here again for the second sequence. The observable state says that Monday is warm, Tuesday is cold. And then I will calculate the probability of having sunny and rainy in these 2 consecutive days. The initial probability of having sunny in the first day is 0.67, right? This is what we defined before. Just go back to the previous few slides. We have defined this 67% chance the first day will be sunny. So I use this initial probability as to start, and then since we want to calculate the probability having a sequence of sunny, rainy, so based on the emission probability, we know that the probability of having tomorrow rainy, knowing that today is sunny, just look at the previous few slides, is 0.2, it's 20%. So I write it down here, 20% a chance of this sequence to occur. And then we calculate, we put the emission probability, because in this scenario I say the first day is sunny and the first day is Monday, and Monday the temperature is warm. Based on the emission probability that we defined before, the probability of having warm temperature given the weather is sunny is 80%. So I put it here. Now for tomorrow, for Tuesday, because I want to calculate the sequence of sunny, rainy, Tuesday will be rainy in this case, and Tuesday, the observable state of Tuesday is cold. So emission probability of having a cold temperature given a rainy weather is 60%. We discussed this in the previous few slides. So this is our number. So these are all probability numbers in these 2-day scenarios. Now, the total probability of all of this event to occur is the probability of having a sequence sunny, rainy combined, and at the same time the temperature of these 2 days are warm and cold, is equal to the probability of having this sequence sunny, rainy, given that the temperature sequence is warm, cold, multiply by the probability of having this sequence of temperature, warm and cold. So we calculate this. This will be equal to 0.67 times 0.8, right? How do I get this? This is just based on the conditional probability, right? Times the probability of having warm, cold. Again, another conditional probability we calculated here, and then we multiply these two. It's equal to 0.064. This is for one scenario of having a sequence sunny, rainy. Then we have to calculate the same thing for the remaining three scenarios, having sunny, sunny, rainy, sunny, and rainy, rainy. I have already calculated. Please try it by yourself. Check it. How did I come up with these four numbers? 0.064 is the one that we just calculated before. You can try it by yourself for the other three. In case I also made a mistake, you can check it by yourself. So from these four scenarios, we just select the one with highest probability. In this case is the first one, 0.085. So we can conclude at this point that the highest probability that the weather is sunny in these two consecutive days is the highest. So the highest probability is that the weather will be sunny. Okay, this is the maximum likelihood in these four scenarios. I hope to this point everything is more or less clear. What I haven't discussed yet is, in practice, how do we get this number? How do we get these numbers? The emission probability, the transition probability, the initial distribution. How do I get this number? Again, all of these numbers are statistic number, stochastic number. So what you have to do, you collect this historical data. So in this case, for instance, I collect 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 31 days. I have a history of 31 days. I collect how the weather in these 31 days, in this 1 month. The first day is sunny, rainy, and so on and so forth. And at the same time also record the temperature reading, warm, cold, etc. and so forth. And then from here we can derive the emission and transition probability. So let's take a look on the weather sequence here. We calculate how many of this sequence that have transition from sunny to sunny. So from here we have 1 from sunny to sunny, 2, 3, 4. Okay, we have 4 and this is not counted. And then now we have another sunny here, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 transition from sunny to sunny, and then how many sunny days? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, I don't count the last one because the last one is just the to make the transition complete. So I have 20, so there are, how many was it before? 16 out of 20, so 16 out of 20 is 80%, so there is a chance, there is a probability of having tomorrow sunny, given that today is sunny, of 80%. And then same thing, we have 20 sunny days, how many of them will have a transition to rainy? So this is 1, sunny to rainy, 1, sunny to rainy, 2, sunny to rainy, 3, sunny to rainy, 4. We have 4 occurrences out of 20 sunny days. Okay, so 4 out of 20 is 20%. Then you do the same thing for rainy to sunny, rainy to rainy, and from there you can get all of the transition probabilities. Based on these sequences, you can also find the emission probability. So from all of this data, you calculate how many of sunny day that will give a warm temperature. We have 1, 2, 3, 4, not this one, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 out of 20 sunny days. So we have 80% probability of that. And then same thing, you count how many cold temperature given the weather is sunny, and then you calculate the probability. Of course, intuitively here, the more historical data that you have, the more representative the probability number that you will calculate. Okay, so this is how we came up with the emission and transition probabilities. And previously we discussed already an example of a 2-day event case, how to predict the hidden state on a 2-day event case. In the next few slides, I think I will record it in another video. We will discuss on how to evaluate when we have more than 2-day sequence case. Okay, the calculation might be a bit complicated, but it's still doable.